sklearn, linear model, MultiTaskLassoCV. Description: MultiTaskLassoCV is a linear model that learns a sparse solution for multiple response variables. It implements the multitask lasso with L1 L2 penalization. Using cross-validation to choose the best regularization parameter. It is suitable for problems where the response variables are correlated and it is desirable to learn a shared set of features. Inputs: X a 2D array representing the training data, where each row corresponds to an instance and each column corresponds to a feature. Y a 2D array representing the target values for each instance, where each column corresponds to a different response variable. Outputs: Coa a 2D array containing the coefficients of the learned model. The shape is n features, n tasks. Intercept a 1D array containing the intercepts of the learned model. The shape is n tasks. Steps: The model uses cross-validation to find the best regularization parameter for the multitask lasso. For each fold in the cross-validation, the model fits the data using the current regularization parameter. The model then evaluates the performance on the holdout fold using a specified metric. The model selects the regularization parameter that yields the best performance across all folds. The model fits the entire training data using the selected regularization parameter to learn the final model coefficients. Metrics: R2 coefficient of determination, a measure of how well the model predicts the target values. Mean absolute error, a measure of the average absolute difference between the predicted and actual values. Visualization plots: Coefficient plots plot the coefficients of the learned model for each feature and task to visualize the sparsity pattern and the relationship between features and response variables. Prediction plots plot the predicted values against the actual values for each task to visually assess the model's performance. Fine-tune parameters. Alpha is a list of regularization parameters to be considered by the cross-validation CV, the number of folds to use for cross-validation. Fit intercept, whether to fit an intercept term. Uncertainty methods. Bootstrap resampling, repeatedly draw samples with replacement from the original data and fit a model to each sample. The distribution of the model coefficients across the bootstrap samples can be used to estimate uncertainty. Bayesian methods incorporate prior information about the coefficients and use Bayesian inference to estimate their posterior distributions. The uncertainty is captured by the width of the posterior distributions. Challenges and fixes. Challenge 1: Overfitting. The model might overfit the training data if the regularization parameter is too small. Sample use case: A model trained with a small regularization parameter might have high accuracy on the training data but perform poorly on unseen data. Fixes: Increase the regularization parameter to encourage sparsity and prevent overfitting. Use cross-validation to select the best regularization parameter. Challenge 2: High dimensionality. The model might struggle to learn accurate coefficients if the number of features is much larger than the number of samples. Sample use case: A model trained with a large number of features might have poor performance due to the curse of dimensionality. Fixes: Use feature selection techniques to reduce the number of features. Use dimensionality reduction techniques such as principal component analysis (PCA) to reduce the number of dimensions. Consider using a different model that is better suited for high-dimensional data, such as a random forest. Challenge 3: Multicollinearity. The model might have unstable coefficients if there is high correlation between features. Sample use case: A model trained with highly correlated features might have different coefficients for each fold of the cross-validation. Fixes. Use feature selection techniques to remove highly correlated features. Consider using a different model that is more robust to multicollinearity, such as ridge regression. Use regularization techniques, such as lasso or elastic net, to penalize large coefficients and reduce the influence of highly correlated features.